Hi, it's time for another math easy solution. Trying to discuss further into trigonometric integrals and now look at trigonometric substitution in solving integrals. Basically, I'll go over an introduction right now. In finding the area of a circle or an ellipse, an integral of the form like something like this may arise, and so square root a squared minus x squared dx. And in this case, well, a is greater than 0 because the inside the square root can't be negative. Now the integral of this, it's not straightforward, but if it were in the form of something, let's say we had an x in front of it, so x, and then we have a squared minus x squared, and then a dx right here. Now, if we had it in this form instead, we could use this substitution, which is let u equals to a squared minus x squared, and the reason for this is the differential du is going to equal to, well, this just equals to negative 2x dx. So now in this case, we've covered these two right here, and also this this entire thing is gone. So if we plug that in, well, this dx here becomes x dx equals to 1 over 2 negative. Now this whole integral becomes negative 1 over 2 square root of the square root of u, and now we have a du. So as we have something like this, and we can solve this integral. But the problem is so this one we can solve this, but in the first integral we still haven't found out how to solve this, and as it stands, the first integral is more difficult. But now we'll try something else. If we apply a trigonometric substitution in this form, let's say let x equals to a times it by sine theta. So now we're changing the x variable to theta. And the reason we're doing this is because basically the square root a squared minus x squared, this becomes a squared minus, now we plug this in, a squared times it by sine squared theta. And now we could take the a's out, so this will be a squared times by 1 minus sine squared theta. And now, as you can see what happens here, we could apply the trig identity, and now this equals to cos squared theta. This is just rearranging trig identity to get this. So if we get that, this becomes a squared times by cos squared theta. And now we could actually get rid of the square root sign. So now this equals to a, this square root of a squared is a, and now we have a cos theta, except in this case this has to be absolute value, because the original integral right here, this square root, this can't be negative inside. So, and this is always positive for real numbers. So if it's positive and we're given that a is greater than 0, basically this has to be positive as well. So that's why it has to be positive. I'll just write that it's positive because a is greater than 0, and square root a squared minus x squared is also greater than 0. Greater than or equal to 0. And as you can see, applying this trig substitution, we're able to simplify it and remove the square root. So now basically we've settled the first part, and when you throw this into the integral, as you can see, it's simplified, so we could eventually solve the integral. And now to recap on the two substitutions we used, if you notice the difference in between the two, the first substitution which we used was, for this case, u equals a squared minus x squared. The new variable u is a function of the old variable x, so we had u equals to a squared minus x squared. But now in the second substitution, or the trig substitution right here, we started off with the old variable as a function of the new one, theta. So we had x equals to a sine theta. And it is important to notice the difference. So now basically in general, if we make a substitution of the form x equals g of t, by using this. Basically we make the substitution by using the substitution rule in reverse. So instead of having a new variable like this, you use the old variable as it. So basically it's like a reverse of the substitution rule. And also I'll illustrate this further. To make our calculation simpler, we assume that g has, or this function g of t has an inverse function, that is g is a 1-to-1 function. So make sure to see my earlier video on 1-to-1 functions in the video links below. Basically 1-to-1 is just something like this. If you have a function like this, etc., and for each y value there is only one x value. So there's an x, there's a y. So that's 1-to-1 versus something that's not 1-to-1. If you had something like this, if you had something, let's say like a trig function like that, as you can see here, for one y value here there's a y, but now you have multiple x's. You have x, you have x, you have x, etc. There's an x. So you have in this case 4 x values for one y value. And the problem here is when you take the inverse is we switch the x and y. In this case we can't switch y with 4 x's, and we'll need to do this inverse because basically after you start solving this we would need to apply an inverse in the integral, and I'll go through that in an example later. Now in this case, when we use the substitution rule in reverse, we can write the original substitution rule. And the original is basically when you let u equals 2 a function, you let u equals g of x. So in this case we're gonna get now, and also the differential is gonna be du is equal to g prime of x dx. And this solves a function that if you have something like this, g of x times it by, actually no, this is f of g of x. This is to simplify it. G prime of x dx equals 2. So now when you apply the substitution rule, this becomes du, and now this inside is u. So this just becomes integral of f of u du. So this is just simplified like that. But in our case we're going to be rewriting it to have it in reverse. And when we do that, we replace u with x and then x by t. So this becomes, in this case we'll write this first because we're doing it reverse. So u is becoming x. So f of x dx is equal to, now when we apply x equals g of t, this becomes now, well, f of g of t, and then this is g prime of t dt. So as you can see, we're just doing this side we're going from here to here, this now we're just going reverse, and that's in this case right here. So we're reversing it. Yeah, I'll just write that better. So now in this case when we go reverse, that's this case. And that is pretty much what we're going to be doing with trig substitutions. And this kind of substitution is called inverse substitution. Now in the case that I went over earlier, basically we can make the inverse substitution x equals a times sine theta, provided that it's defined as a 1-to-1 function. And this can be accomplished by restricting theta to lie between this integral from negative pi over 2 to pi over 2, or written like this. This equals to, this is just a closed interval, meaning less than equal to, this is theta less than equal to pi over 2. So now for this interval we could apply this, and we also have to switch the interval if you're writing like some sort of numerical calculation, etc. So now in this case this is a 1-to-1, because when you look at the sine function, it's something like this. The sine function looks like this, and it keeps going down and etc. And I'll draw this dashed line like that. And at this point right here, this is at negative pi over 2, and this is at right here at pi over 2. So as you go past this, as you can see, this point you'll have a 1-to-1. I mean, you won't have it 1-to-1. If you go past, you're gonna have equal values. So now we just separate it, so we're only dealing with from here to here, so that they never cross. When you draw a horizontal line using the horizontal line test, only crosses once. So that's what we'll be dealing with for when we use this substitution. And now in the following table is a list, well, I'll write this down, is a list of trigonometric substitutions that are effective for given the radical expression. Radical is just has the square roots, etc. powers, because of the specified trig identities. And I'll go over those soon. And basically in each case, the restriction on theta is imposed to ensure that the function that defines the substitution is 1-to-1. I'll go over that too. And these are the same intervals I used in my earlier videos on inverse trig functions. Basically these, when you're dealing with inverse trig, you have to make sure it's 1-to-1. So now if we have the expression right here, which is, so if we're dealing with an integral that has a square root a squared minus x squared, we would apply the substitution. I'll just put this line like this, and we'll apply the one we just applied earlier. So a sine theta for the interval theta is less than pi over 2, greater than or equal to negative pi over 2. And the identity we use is just 1 minus sine squared theta is equal to cos squared theta. And now the second expression, another useful one, is if we're dealing with, let's say, the addition of these two. So a squared plus x squared, we could apply a and x equals a tan theta. And now the reason, now for the interval for this one, when we look at the function of tan, it's going to be something like this. So it's going to look something like that. It goes to infinity at these intervals right here. This is at pi over 2. This is at negative pi over 2. And again, it's a trig function, so it repeats everywhere. But we're only dealing with this part right here. And this goes like that. So we're just going to be dealing with in between here, and this is where x is less than pi over 2 because it can't equal it, because it goes to infinity, and greater than negative pi over 2. And now the trig identity that we will use is this one, which is 1 plus tan squared theta equals 2 secant squared theta. Let's go around this, and now the last expression that we might come across, or the last useful one that comes across a lot, is this one here, x squared minus a squared. So if we have this right here, we would apply x equals a secant theta. And now when we look at secant, this is basically equals to, well, 1 over cos theta. That's just this one right here. So we'll apply this one, and this just here for reference. So to find out the intervals, if we look at the function right here, how it looks something like this. So if we were to draw out the cosine theta, so it's going to be something like this. This is a cosine theta curve. It starts off like that, etc. So now this is the just 1 divided by cos theta. So basically we divide this by itself at every point. I mean, we divide here. I mean, we would go 1 divided by at this point. So this is 1. So we start off here. So 1 divided by 1 is that. So at this point here where it goes to 0, 1 divided by 0, that goes to positive infinity. So it looks something like this. And so this is how the curve would look like, and this is at this right here. So this is how the secant function looks like. So this is again secant of x, and now at this point here it will be the same thing. It's negative 1, so it's going to go down like that. It's going to go down to infinity, etc. So I'll just draw it like that. So now in this case, so what my calculus book uses as the interval is between these two right here, between this and right here. So this is what the interval it uses. And at this point here, that's pi over 2. So this is pi over 2. At this point right here is pi. Yeah, this is just pi. And at this point right here is 3 pi over 2. So the interval is going to be, it's a two-part interval, so it's going to be from, it's less than equal to 0, so that's this point. There's theta. Now less than pi over 2, because it can't equal pi over 2. And then or using, now because this has two intervals, so it could be in this case or the second case, which is from here, which is, well, pi is less than equal to theta and less than equal to 3 pi over 2. So this is the intervals that my calculus book uses for inverse of secant of x. And now the identity we'll use is basically the same thing as this, but rearranged. So this would be secant squared theta minus 1 equals 10 squared theta. And basically, yeah, these are the three, this is a table of the three expressions we'll deal with in the examples. Anyways, that's all for today. Hopefully you'll learn from this pretty extensive introduction to trig substitution. But it's pretty useful, and I'll go over some examples to further illustrate this in later videos. Anyways, thanks for watching. Like always, you can download these exact notes in the link below, and stay tuned for another Math Easy solution.